Hey guys, welcome to this live stream. Today I'm going to talk about something really cool, which is, as soon as I heard about it, I was very fascinated and I wanted to share it with you guys. It's called quantum bomb detection. I heard about this, or I studied the paper that explains this like a month ago, and I've wanted to make a video about it ever since. And I was thinking, how can I explain it? Before I explain this quantum bomb detection, I have to tell you a little bit about quantum mechanics. You have to basically get a little bit of what quantum mechanics is before you can start to understand this. So what this quantum bomb detection thing says is that you can actually measure things without looking at them. You can measure something or know that it's there without interacting with it. And this is very weird. When you look at something, light is bouncing around and it hits that object and it comes back to your eyes. But when you do this quantum bomb detection thing, you actually measure something, you basically look at it without light. So how does that work? Or without light really touching it. So let's first explain what quantum mechanics is in a quick way so that we start to understand how this thing is really weird. So quantum mechanics starts with the idea of, or with the question of what is a state? What is a state? How do you describe the world? So I have the state of this room, it's in some state, and how do you describe it? And in particular, how do you describe it mathematically? And when you get to the description of the state, that's where you start to realize how quantum mechanics is weird. So let's start with classical mechanics. I want to describe the state. I can say this pen is here, that pen is here, that pen is here. There's a fly flying around. For example, I can say it's over there, now it's over there, then it's over there, and I can describe its speed. So I can describe the state of something by telling you where it is at each instant. And that, let's just call that like x of time. So in classical mechanics, or classical physics, this is the domain of our normal intuition, classical physics. And just because it's classical physics doesn't mean that it's obvious to us. Like, even classical physics took thousands of years to get to. Even Aristotle got it wrong. It took thousands of years to get to Newton, who found like correct laws that made sense, and they're still hard. Like when I teach people classical physics, it's still hard. But quantum mechanics, compared to that, is even more non-intuitive. That it might not be harder, but it's less. It's harder to picture. So here's the state in classical physics. In quantum mechanics, you take whatever the state is. Let me simplify this. So this position, let's say there's only 10 positions. There's 1, 2, 3, 4, 5, 6. Let's say there's 1, 2, 3, 4, 5, 6, 7 positions. And if there's a particle, maybe at one point it's here, then it moves there, then it moves there, maybe it moves back. So classical physics just becomes describing at each instant, where is that particle? Is it in this box, or that box, or that box? And then you can say it's in the state 1, in the state 2, in the state 3, in the state 4, in the state 5, in the state 6, and state 7. So there's 7 states that the particle can be in. Here, or here, or here, or here. In quantum mechanics, it says for any possibilities, for any one of these possibilities, the state can be in a mixture of those states. So what does that mean? That means that a particle can be, ignore what this square root of 2 is for now, but a particle can be in this state, and we represent it by psi. Psi is just a name for the current state of the world. And you represent it like this. It can be a mixture of the possible states. In classical physics, it's just one of them. But in quantum mechanics, it's a linear superposition, or it's just like a number times one of them, times another number times another one, and so on. Okay? So this what does this mean? Well, when I tell you it's in 1, you understand what that means. When I tell you it's in 2, you understand what that means. But when I tell you it's in this thing, what is that thing? Well, this just says when you make a measurement, when you send the light to interact with the electron or with whatever this particle is, whatever thing you do to determine the state of the particle, there's a probability, which is this thing squared, which is 1/2, and this thing squared to be found in 1, and this thing squared, which is 1/2, to be found in 2. So when you're in this state, there's a probability to be found here and a probability to be found here. And what is really weird is that this is not a statement about, well, maybe it's in 1, maybe it's in 2, and I don't know which one it is. No, it's in this state. The statement in quantum mechanics is that the universe or even God does not know anything about anything other than this state. So all you can say about the particle is this thing. You can't say it's in 1 or 2. And when you make a measurement, it's probability that it will be 1/2 in the first one, and there's half the other time it will be in the second one. But before you did the measurement, what state was it in? It was in this state. You have to write it like that. And that's why, by the way, there's a square root of 2, because you take whatever this probability is and you square it, and this and you square it, and then they have to add up to 1 if you do all the probabilities, because probability usually has to add up to 1. And this mathematical fact has a lot of consequences in quantum mechanics, actual physical consequences when you try to work it out. But anyway, so this is the basic idea. And then I want to tell you another element that makes it even stranger is how things evolve in time. So I already told you, classical physics is this picture. You're here, you jump here, maybe you jump there, or you go back. So this is the kind of evolution. But as we just said, this is the state in quantum mechanics. So what does this do with time? So the idea is that there's something called quantum superposition. Let's say that there is a state that you started in. It could be this one. Let's just say this is psi 1. This one, and if you evolve it in time, it goes to another state, which is 1/2 let's say maybe 3 and plus, actually I'm gonna make it simpler, sorry about that. So let's say at t equals 0 seconds, that whatever the evolution is, it says that this state is going to interact with the surrounding and evolve into this state at t equals 1 second. Alright? And then I have another state which is the same as this one but with a minus sign here. Okay? And maybe this evolves into the state 4 at t equals 1 second. And this is 0 seconds. So if you start there, you end up there. If you start there, you end up there. So this is the kind of evolution that you have to give. Whenever you need to specify the laws of physics, you need to first say, how do I describe things? How do I describe states? Well, you describe, this is kinematics. We already said this is how you describe a state. But then dynamics or evolution, you describe it with this. You say, you want to say, if I start in one state, where is it going to end up? Okay? But the thing about quantum dynamics is that it's linear. And that means, okay, I was in this one and this one. What if I started in this one plus this one? If you add the initial states, then it just tells you at 0 seconds, all it tells you is you have to add the final states as well. So remember this 1 over square root of 2 because of normalization. So when you add these, you have to also add the final states. And that would give you 1 over 3 plus 1 over square root of 2 times 4. Okay? And remember, the addition of these two, because there's one of them is plus, one of them is minus, if you work it out, it's just going to be 1. So 1 goes into this. This is the evolution of 1. Okay, so if you know these two things, then you are ready to understand quantum bomb detection. And if you're just tuning in, or if you missed the beginning, we're trying to understand how you can measure something or see something without actually interacting with it. So you can't, usually when you see something, you send light to it, it hits it and comes back to your eyes. But we're trying to see something without actually anything hitting it. So let's see if we can do that. So the measurement is like this. You have a light that comes in, and it passes through a partially reflecting mirror. So part of the light goes up, part of the light goes here, okay? And here there's a mirror. And then there's another partially reflecting mirror. Partially reflecting means half of it goes this way, half of it goes through the mirror. So here we go like this, and then, well, I guess should be, the mirror should look like this, so that part of it goes here, and part of it goes there. Okay? And there's a detector here to measure the state of the final electron, or the final state of the light, and there's another detector, D1 and D2. There's another detector here, okay? Now here's the issue. Here's the key point. What we're gonna say is, you start in a state which is 1, okay? But this state ends up, part of it goes into 1, it's still moving like this, and part of it is in the second state, which is going up, okay? And actually, when you reflect off a mirror, this becomes 1, but you also multiply by a minus sign. This is a known fact that when you reflect off a mirror, the wave changes its phase. But if you're not familiar with that, all you can just believe me that there's a minus sign when it crosses like this, okay? And then there is number 2 here when it goes through there, okay? And then okay, so then you have this 1, 2, and this is going to go through the mirror, so it's going to be minus 2. And this one is going to go through the mirror, plus 2. So maybe you didn't follow all these letters in what I'm saying, but all you need to know is when they went, all you need to know is that when the two lights went and got to the detector, one of them was in a state plus 2, the other one is in a state minus 2. And remember that in quantum mechanics, what I just said, because of superposition, when you add the initial states, when you start with this thing plus this thing, the final result is the final result of the first one plus the final result of the second one. So what this detector, D1, will measure nothing. Because it came in a state 2 plus 2 minus 2. and that's 0. And the first detector, the second detector is going to measure the whole thing. So it will always, so D1 will measure nothing, D2 will always measure. Will always detect a photon. Okay, so this is cool. This is where we're starting from. But what does this imply for the bomb detection? Well, here's the trick. And this is going to seem silly to you, but what we're going to do is we're going to put a bomb here. Bomb. Okay, this bomb will always explode if anything touches it. So if this photon goes there and touches the bomb will explode. But if it goes there, the bomb will not explode. But this is a weird situation because we already said that in quantum mechanics the state splits into these two. So there is part of the wave function that goes to the bomb and disappears because there's an explosion. And there's always part of the wave function, like there's one part that let's say 1 plus 2. This part always goes to the bomb and disappears, okay? And so it doesn't reach here. And then, but this part, which is 2, goes through the detector and is not touched. Okay? So here's the trick. Can anyone guess what is going to happen next? What will change from this situation? So what will change is that basically, remember that in the first case, without the bomb, we got the +2 and the -2. But now we killed off this part, and or that part. We killed off one of them, and then you just have one left. So it's not 0 anymore. And now all of a sudden, detector 1 will measure sometimes. Will measure something part of the time. So initially, the final state was detector 2 always happening because something got cancelled here. But now what we have is something between detector 1 plus between detector 2. This is the new final state. And sometimes you will observe something in detector 1 after you put the bomb. But the bomb is not exploding. Like when you measure something, there is a path, in this path, where the photon went here and nothing cancelled it and D1 gets detected. So actually nothing touched the bomb. And this is the thing that is very confusing, and you should be very confused at this point if you weren't already. So what it says is that the photon went here and nothing interacted with it, and then it went to detector 1. But in this weird way, you could know that the bomb is there even though the bomb didn't go off. And remember, the bomb goes off if anything touches it. So if a company comes and tells you, I have a bomb, and it's very sensitive, it's very easy to trigger, and I want you to make a test that will see if the bomb is working or not, because some of the bombs are defective, and you need to check which ones are which. But how can you test if a bomb is defective or not without interacting with it? So this actually does that. All you need to do is bring this setup where without the bomb, something will go through, and you will get, and you will never get something in the first detector. You will never get this part. Then, because of quantum superposition, the bomb adds or takes away part of the wave function, and then you all of a sudden sometimes measure in D1. But you measure something in D1 even though the result of your measurement is that the bomb is not exploding. So I hope this made sense. I hope you understand it a little bit better. In the future, I'm gonna make more videos about this, about quantum mechanics and quantum field theory, because I think there's a lot of cool things about them. Not that the rest of physics is not cool. Like classical physics, there's so many beautiful things that you can do, like pattern formation and how things collect together, and complexity, and biophysics. So there's a lot of cool things, other cool things that you can learn. But there's a lot of also very interesting and intriguing things in quantum mechanics and quantum field theory, and it's very weird that these things are true. So it will give you a lot of insight into the world when you really understand what these things are. So thank you for sticking around, if you're sticking around, and I'll see you next time.